Imagine an object so massive and energetic that it doesn't just pull you toward its center, but actually drags the very fabric of space and time along with it like a giant whirlpool. This is the reality of a Kerr black hole, a rotating gravitational monster that houses a reservoir of energy so vast it defies conventional human comprehension. Physicist Roger Penrose proposed a theoretical mechanism to tap into this reservoir, effectively turning a black hole into the ultimate engine by stealing its rotational momentum. Known as the Penrose Process, represents one of the most extreme applications of general relativity, suggesting that an advanced civilization could fuel its existence for eons by scavenging the kinetic energy of a dying star. Understanding how this works requires us to discard our everyday notions of geometry and motion. To grasp the Penrose process, we first have to look at the unique anatomy of a spinning black hole, specifically a region called the ergosphere. Unlike a static Schwarzschild black hole, which is defined simply by its mass and event horizon, a Kerr black hole possesses angular momentum. As the black hole spins, it exhibits an effect known as frame dragging, or the Lense-Thirring effect. Space-time is not a static stage upon which matter moves. It is a flexible medium that can be twisted and pulled. Within the ergosphere, the dragging is so intense that it is physically impossible for any object to remain stationary relative to the outside universe. Even if you had a rocket engine with infinite thrust, you would still be forced to orbit in the direction of the black hole's spin. This isn't because of a physical force pushing on you, but because the very geometry of the universe has become a one-way street. The ergosphere exists outside the event horizon, meaning that while you are trapped in a rotational flow, you are not yet doomed to fall into the singularity. You can still escape. And it is this accessibility that makes the Penrose process possible. The genius of the Penrose process lies in the oddity of negative energy states. In our daily lives, energy is always a positive value. Kinetic energy, potential energy, and mass energy all contribute to a positive total. The mathematics of general relativity allowed Penrose to discover that inside the ergosphere, a particle can technically have a negative energy relative to an observer at infinity. This isn't science fiction or exotic matter. It's a consequence of the coordinate system being so severely warped that the time-like and space-like components of the metric swap roles in a specific way. If you enter the ergosphere and split an object into two pieces, you can arrange the trajectory so that one piece falls into the event horizon, while the other is ejected back out into space. If the piece that falls in is on a negative energy trajectory, the piece that escapes will emerge with more energy than the original whole object started with. Effectively, the ejected fragment has stolen a portion of the black hole's rotational energy. To visualize this, think of a massive flywheel spinning at nearly the speed of light. If you throw a weighted ball at the flywheel and it somehow bounces off in a way that slows the flywheel down by a microscopic fraction, that energy has to go somewhere. In the case of the Penrose process, the black hole is the flywheel. Every time a particle with negative energy is swallowed, the black hole's total mass energy decreases and its spin slows down slightly. The energy gain isn't coming from nothing. It is a direct withdrawal from the black hole's rotational bank account. The theoretical limits of this process are staggering. Calculation shows that through this method, we could extract up to 29% of a black hole's total mass energy. For a black hole with the mass of our sun, that equates to an amount of energy billions of times greater than the total output of the sun over its entire 10 billion year lifespan. It is the most efficient form of energy conversion imaginable, dwarfing nuclear fusion, which only converts a fraction of 1% of mass into energy. This realization shifted our view of black holes from being cosmic trash cans to being the most potent power plants in the universe. While the original Penrose process involves discrete particles or objects, Later refinements suggested even more powerful versions of the concept. Roger Blandford and Znajek proposed that magnetic fields could do the heavy lifting. Most black holes are surrounded by an accretion disk of hot plasma. As the black hole spins and drags spacetime, it winds up the magnetic field lines of this plasma like a giant spring. This creates a sort of electromagnetic version of the Penrose process, where the black hole's rotation drives massive jets of radiation and particles away from the poles at nearly the speed of light. These are the same relativistic jets we observe in active galactic nuclei and quasars, visible from billions of light years away. Nature is already using the Penrose process to light up the cosmos. We are simply observing the mechanics of it. The implications for a sufficiently advanced civilization, often categorized as a Type 2 or Type 3 on the Kardashev scale, are profound. If a species could build a structure around a rotating black hole, such as a modified Dyson sphere, they could theoretically survive long after every star in the universe has burned out. In the deep future of the universe, during the black hole era, these gravitational engines might be the only remaining sources of light and heat. A civilization could drop waste matter into the ergosphere, split it, and harvest the high-energy recoil to power their cities and machines. It turns a black hole into the ultimate recycling center, where trash is converted into pure energy, usable power with merely 30% efficiency. However, there are massive engineering hurdles that make this purely theoretical for now. The ergosphere of a stellar mass black hole is a region of extreme tidal forces and intense radiation. Any ship or mechanism entering this zone would be subjected to spaghettification or incinerated by the surrounding accretion disk. The timing required to split an object onto a negative energy trajectory is incredibly precise. You would need to be traveling at relativistic speeds and execute the maneuver with sub-millisecond accuracy. Even if we could build a material strong enough to withstand the environment, the navigation alone is a feat beyond our current capabilities. The physics holds up. The Penrose process isn't just a mathematical trick. It has been tested through computer simulations and even analogous laboratory experiments. Physicists have used water tanks and sound waves to simulate the conditions of a rotating black hole. By creating a vortex in a fluid and observing how waves scatter off the rotation, researchers have seen wave amplification that mirrors the energy gain described by Penrose. This suggests that the fundamental principle of extracting energy from a rotating system via frame dragging is a universal law of physics, not just a quirk of Einstein's equations. There is also a variation called the super-radiant scattering, or the black hole bomb. If you surround a rotating black hole with a spherical mirror, you could trigger a feedback loop. You send an electromagnetic wave into the ergosphere. It gains energy through the Penrose process, reflects off the mirror, and goes back in to gain even more energy. This would continue exponentially until the energy density becomes so high that the mirror shatters, releasing a massive burst of energy. This outlines the potential for black holes to act as high-capacity energy storage systems, or perhaps even weapons on a galactic scale. The beauty of the Penrose process is that it forces us to reconsider what we mean by a hole in space. Far from being empty voids, spinning black holes are dynamic, active participants in the evolution of galaxies. They are the engines of the most violent events in the universe. Yet, they also offer a blueprint for the ultimate sustainability. When we look at the massive black hole at the center of our own galaxy, Sagittarius A star, we are looking at a spinning battery containing more energy than all the stars in the Milky Way combined. We are currently in the infancy of our understanding, barely able to capture an image of an event horizon. Yet, the math tells us that the keys to the kingdom are hidden in that warped space. As we refine our theories of quantum gravity and improve our observations of distant quasars, the Penrose process remains a beacon for what is possible. It bridges the gap between the abstract geometry of general relativity and the practical needs of a future civilization. It reminds us that in the universe, nothing is ever truly lost, only transformed. Even the most formidable gravity can be outsmarted if you understand the rhythm of the spin. By learning to dance with the curvature of time, we might one day harness the very force that appears designed to destroy us. The transition from being subjects of gravity to masters of it is the ultimate challenge for any intelligent species, whether or not we ever build a Penrose engine. The fact that such a thing is even physically allowed tells us something fundamental about the generosity of the cosmos. It suggests a universe where even the darkest places are filled with the potential for light and movement. As long as there is rotation, there is energy. And as long as there is energy, there is a way for life to persist against the encroaching cold of the void. This process represents the pinnacle of thermodynamic efficiency, turning the weight of a star into the momentum of progress. It is a reminder that the laws of physics are not just barriers. They are opportunities for those with the curiosity to untangle them. To imagine the Penrose process is to imagine a future where the end of the stars is not the end of the story, but merely the beginning of a different, much grander era of existence. We are still millions of years away from needing this energy, but the groundwork laid by Penrose gives us a destination to aim for. It proves that the universe is not just a collection of objects, but a complex system of gears and levers that can be understood and eventually operated. The black hole, once a symbol of inevitable doom, becomes a symbol of ultimate potential. If we can solve the riddle of the ergosphere, we can solve the problem of survival in a dying universe. This is the promise of the Penrose process, a testament to the power of human thought to penetrate the most extreme environments in nature and find a way to thrive within them. It challenges us to think bigger, to look beyond our solar system, and to recognize the massive scales on which the universe operates. By studying these gravitational giants, we learn not just about the death of stars, but about the fundamental mechanics of energy and time itself. The Penrose process is our roadmap to the stars, a theoretical bridge across the most hostile terrain in existence, leading to a future where we are no longer bound by the limits of our own sun. Explore the math. Look at the stars. And remember that even a black hole can give back if you know how to ask.